All right, let's get started with 4.2, polynomial functions of higher degree. So, polynomial functions are anything of this form. So, basically what we're talking about is any sort of x with a power, so x to the fifth, something like that, plus or minus another x, so maybe x to the third, and then minus coefficients are fine, so minus 2x, and then constants at the ends are fine as well, so something like plus 7, something like that. Okay, there are two situations where you're not going to be a polynomial. If, in any case, you have a negative power, or a fractional power. So if you have x to the negative 1, that is not polynomial. If you have x to the 1/2, that is not a polynomial either. Okay, 1 over x is the same as saying x to the negative 1. So if you have a variable in the denominator, not a polynomial. Square root of x, same thing as x to the 1/2. So if you have a radical with a variable underneath it, not a polynomial. Everything else is. All right, so let's walk through these. So we'll say whether these are polynomials or not, and then we'll say what their degree is. So remember that the degree is the biggest power you can find. So for A, yes, degree is 5. For B is a no. See that square root? C, this is a yes. Okay? Because you could write this as 2x to the 0. So our degree here is 0. For this one, this is a yes with degree of 2. This is a yes with a degree of 7. The reason why is this is not in general form. If you were to multiply this all the way out, you would end up, well, you would distribute, you would have to FOIL, you would do a few things, but you would end up with an x to the 5th times an x squared, which would get you an x to the 7th. So this is a degree of 7. And then this last one is a no. The reason why, I found the negative. See if you can do it. First one is a no because of the fraction. The second one is a yes. And did we figure out what the degree is? 8. 2 more is 10. 3 more is 13. The degree here is 13. All right, so the graph of polynomials are smooth and continuous. So here's some examples of things that are not. So this first one here is not continuous because of the jump. The second one, not continuous right here. There's a little hole. They were graphing along and then skipped right over. Very similar to a jump. The graph of this one is continuous, but it's not smooth because of these hard edges right here. You can't do a V shape at any point. So the absolute value of x is not a polynomial because the graph is a V. Would not work. So nice, smooth, and continuous graph. If you have nice curves and no jumps at all, you are a polynomial. Okay, power functions. The power function is simply a polynomial with one term. Okay, one term. So if you had y equals 5x to the 4th, that's a power function. Okay? If you had y equals negative 2x cubed, that's a power function. Now, we don't care about this too much other than to say, what does x to the 4th look like? And what does x cubed look like? Remember that x squared, the graph looks like this, right? It's a parabola. And we talked about that x cubed looks like this. What does x to the 4th look like? It looks like this. Okay? Now, if it was x to the 4th plus some other things, it might look like this. But if it's just x to the 4th by itself, it looks almost identical to the x squared. It might be a little wider, a little skinnier. X to the 5th, what does that look like? Almost identical to x cubed. Guess what x to the 7th looks like? Just like x to the 5th and x to the cubed. Now, it's not identical, but the general shape is the same. And the key is that the end behavior is the same. So in the textbook, you've got this. But what this is saying is that end behavior of odd degree go like this. We don't know what happens in between, but at the edges, it's going down on the left and up on the right, right? X cubed looks like that. So an even degree polynomial will look like this, with end behavior going up and up. Now, if it's a negative, it might look like that. So y equals negative x squared looks like that, negative 1 x squared. And negative x cubed would look like this. But the point is that for odd degrees, the ends are going to be going in opposite directions, right? O and O. And for even degrees, the ends are going to be going in the same direction. That's going to help us with our graphs shortly. Okay, so what happens if we want to graph a normal power function that is just transformed a little bit? So remember that any plus or minus inside with x is a horizontal transformation. So this is going to go right 1. Remember that the x is always the opposite. So if I said y equals x cubed, that looks like this. Sorry. Like that. And it goes through 0, 0. It would go through 1, 1. It would go through negative 1, negative 1. So what does this graph look like? It's going to be shifted just 1 to the right. So instead of going through the origin, now it's going to go through 1. Instead of going through negative 1, it's going to go through 0, negative 1. It's shifted over the right by 1. Your turn. See if you can take this graph and transform it from the parent function, the power function. So one thing that might be helpful if you rewrote this as negative x to the 4th plus 1. All right, what does x to the 4th look like? X to the 4th looks like this. What does negative x to the 4th look like? It looks like this. So let's go ahead and put that on the coordinate plane. And we'll talk about this. What is the plus 1 doing? Move it up by 1. So that's just going right here. All right, so because this plus 1 is not inside with the x, out by itself, so that's going to be a vertical transformation. Okay, let's talk about what real zeros mean. So I want to use an example here. So we have x squared minus 1 equals 0. So let's go backwards here. They say the relationship 4 is a factor. So all 4 things here are related to each other. Let's factor this first. So this factors into x minus 1 and x plus 1. Okay, so x plus 1 and x minus 1 are both factors. I'm just going to pick one of them. I'm going to pick this one to start. So if we say that x minus 1 is a factor, okay, then x equals positive 1 is a solution. It is a root. And what you hear more than anything is it's a 0 of the function. Okay? And it is also an x-intercept. Okay? So remember, always the opposite. So if I had this, if I had a factor of x plus 5 is my factor, then negative 5 is the 0, is the root. I could say all of these things. Is the solution, is the x-intercept. Right? Opposite terms. Okay, so let's see if we can find this one. So what we're going to do is we're going to factor. So let's pull out an x here. We're left with x squared plus x minus 2. And what multiplies to negative 2 and adds to 1? How about positive 2 and negative 1? All right, so these are all of our factors. I see 3 factors. And that makes sense because this is degree 3. So the factors should always match the degree. So what are my zeros? It's asking for the zeros. The zeros are 0 from here, negative 2 from here, and positive 1 from here. Your turn. See if you can do it. All right, factor out that x. We're left with x squared minus 7x plus 12. And that factors again to x minus 3 and x minus 4. So what are our zeros? Say x equals 0, 3, and 4. Okay, multiplicity. So we just said that if you have an x squared problem, we need to have 2 zeros. But what if you have a situation where you have x minus 1 and x minus 1? So the zeros are x equals 1 and 1. Kind of repetitive to say it twice, so we're going to say this. We're going to say x equals 1 with a multiplicity of 2. And this is just a fancy way of saying that the 1 shows up twice. So let's see. Oh, one thing I want to add on here with multiplicity. When we graph multiplicity, even multiplicity touches the x-axis. So if we were to graph even multiplicity, we just touch and turn around. Odd multiplicity crosses. So we would have something down and cross. And that should make sense because this is like an x cubed, a negative x cubed. And this here is similar to a positive x squared, where x squared we touch, x cubed we would cross. Okay, so let's find the multiplicities here. So the multiplicities here are 1 with multiplicity of 2 because it's showing up twice. Negative 3/5 from right here with a multiplicity of 7. And that's a plus here, so we're going to say minus 5 with a multiplicity of 1. Your turn. Hopefully you said 0, multiplicity 2, 2, multiplicity 3, negative 1/2, multiplicity 5. And we can go in reverse. Let's create a polynomial from this. So we could say y equals, we say the 0 is negative 2. So we would have to have an x plus 2 squared. We would have to have an x minus 0, or you can just write x to the 4th. And we would say x minus 1 from this one with multiplicity of 1. All right, we're going to take all of that we just learned and see if we can do some graphing here. So when we graph, we're going to label all intercepts. And we're going to use multiplicity and end behavior. So here we go. All right, so use a strategy for sketching this. So first things first, we need to label all the intercepts. So the x-intercepts are the zeros. So we have a 0 at negative 2, x-intercepts. Negative 2, multiplicity of 1, and 1, multiplicity of 2. Now, we also want the y-intercept. So the y-intercept, remember, is when you plug a 0 in for x. So instead of x, we're going to put in a 0. So this is going to be 2 times negative 1 squared is 1. It's going to be 2. Okay, so we have our intercepts. Now let's talk about our end behavior. What's our degree of this graph? The degree is 1 plus 2. The degree is 3. The leading term is positive. So this is going to be very similar to y equals positive x cubed, which looks like this. So I know that my end behavior must be going up on the right and down on the left. I cross at odd multiplicities, and I touch at even multiplicities. So I'm going to cross at x equals negative 2, and I'm going to touch at x equals 1. My y-intercept is 2. Okay, so I have intercepts at negative 2, positive 1, and a y-intercept at positive 2. So can we use those pieces of information and connect the dots to make a nice sketch of a graph? I think we can. Up we go. We're going to cross here. We're coming back down. Now, I went over. I needed to touch. So actually I needed to right here turn around and come back up. Okay? So I'm crossing here at -2, and I'm just touching and turning around at x equals 1. All right, try one. See if you can do it. So x-intercept are going to be 0, multiplicity of 2, and -3, +3 there, -3, multiplicity of 2. Our y-int is going to be 0 squared times 3 squared. So that's going to be 0. All right, so we've got our graph here. Now our degree is 2 plus 2, which is 4. And it's positive out front. So we're going to be going up and up. So let's label our intercepts 0, which is also our y-intercept, and -3. Okay. So we're going to start here. We're going to touch, which means we must turn around. We're also going to just touch here and go through this one. So somewhere in here, we must turn back over. Now, we don't know where that is. We're going to learn how to do that later on in a later section. But for now, just a sketch. Just let it turn over. And remember, smooth and continuous. So connect it just like that. Try one more. So on this one, we have not factored completely. So to do this, we got to factor first. So I see a 2x squared in common. I can pull that out, and I'm left with an x squared minus 8. And on this one, x squared minus 8 is not factorable. So let's find our zeros. From the first one, we have 0 with the multiplicity of 2. And from the inside one, I have x squared minus 8 equals 0. X squared would equal 8. So x would equal plus or minus the square root of 8, which is plus or minus 2 rad 2. Now, square root of 8 is between 2 and 3, because the square root of 4 is 2, the square root of 9 is 3. And on this one, we are going to touch as well, because this, I'm sorry. Nope, we're not going to touch because this is one positive and one negative. So we'll cross on both of those. All right, so let's go ahead and label this. What's our degree? The degree is 4, and it's a positive, so we're going to be going up and up. What's our y-intercept? Let's plug in 0 and 0. So what's 0 minus 0? 0. And we knew that because if the x-intercept is 0, so is the y-intercept. All right, so in between -2 and -3, a little closer to -3, right? We're a little closer to square root of 9. And in between 2 and 3, just like that. All right, so how does this work? We're going to be coming down. Let me make this a little easier. How about my arrow right there? We're going to cross. We're going to touch. And we're going to cross. Let's put my arrow there. And that's what it should look like. Remember that these turns right here, we're not exactly sure where they're happening. All right, one more for you to try. See if you can do it. Put it all together. Factor first, y equals x cubed, x squared minus 4, which factors again to x cubed, x minus 2, and x plus 2. Zeros are 0, multiplicity 3, 2, multiplicity of 1, -2, multiplicity of 1. And your y-intercept is also going to be 0. Go ahead and graph them. Our important points are -2, 0, and 2. We are crossing everywhere. This is an x to the 5th positive, so we're going to finish going up. On the left, we're going down. So let's go ahead. Cross, 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 and there we go. All right, we will go over all of these again in class. See you then.